we will solve GATE 2025 EC problems. A simplified small signal equivalent of BJT based amplifier is given. Here we have a small signal voltage source Vs, and we have to find the relation between V0 and Vs, that is V0 by Vs gain. The current flowing from this small signal source is IB. IB is potential difference between these two nodes by the resistance between these two nodes. IB is Vs minus 0 by Rs plus R pi. Rs. We have to know a small thing. Whenever we are given a small signal circuit, we'll directly let us say this is Vi and this is Rd, this is V0. We'll directly write gain as minus Gm Rd, V0 by Vi as minus Gm Rd, because we have a resistor Rd and the current Gm times Vi is flowing in this direction, is V0. If we have a resistor, if current is flowing top to bottom, then this node potential will be positive and the node potential will be I times R. And if current is flowing from bottom to top, this node potential will be negative and that will be minus I times R. Here the current flowing from ground to V0 is Gm times Vi and the current flowing from V0 to ground is minus Gm times Vi. So the node potential V0 will be minus Gm Vi times Rd. Similarly, in this case, the current is flowing from ground to V0 in this direction. So the V0 potential has to be negative. It has to be less than the ground potential. So V0 will be minus beta IB, the current flowing from ground to V0, beta IB times RL. If we put IB values, it will be minus beta Vs into RL by R pi plus Rs. So V0 by Vs is minus beta RL by RL plus Rs plus R pi. That's first option. In this question, we have to find out the DC voltage, potential difference between source and collector and emitter. For that, we have to find out both potential VE and VC. It is given that beta is 100, IB is 10 microamp. So from this we can find out IE, which is nothing but beta plus 1 times of IB. 101 times of 10 microamp, that is 1.01 milliamps. So VE is IE times of 3 kilo ohms. 1.01 milliamps into 3 kilo ohms, that is 3.03 milliamps. The current flowing here is IE 1.01 1.01 milliamps. So the current flowing here also is 1.01 milliamps. So VC will be 10 volts minus the voltage drop across this 5 kilo ohms resistor. 5 kilo ohms into 1.01 milli. That is 4.95 volts. VCE is VC minus VA. This is 3.03 volts. 4.95 minus 3.03. That is 1.92 volts. Option C is the right answer. And here we have another question. Which of the following statements are true with respect to ideal MOSFET based DC coupled single stage amplifiers having finite load resistor? The common gate amplifier has an infinite input resistance. Common gate will have input at source Vi and output at drain. Clearly we can see that input resistance is not infinity here. So first statement is false. The common source amplifier has infinite input resistance. CG, CS. CS amplifier has input at gate or output at drain. Clearly I is 0 here, so R equivalent is infinity. So the second statement is true. The third statement is the input and output voltages of the common source amplifier are in phase. Clearly this statement is false. Let us say I have Vi here and V0 here. If I increase this node potential, the current flowing will increase. Vi increases, implies GM increases, implies V0 is nothing but minus GM RD times Vi. If minus GM RD increases, V0 decreases. As you increase the input voltage, output voltage is decreasing, so they are 180 degrees phase, they are out of phase. So the third statement is also false. The input and output voltage of the common drain amplifier are in phase. So we know that V0 by Vi of common drain amplifier is GMRD. If I increase Vi, VGS will decrease. That implies GM VGS will decrease. Similarly, V0 is minus GM VGS times of RD. This is already negative, and here we have a 180 degrees, so the resultant will be positive. GMVI times of RD. Here VGS will be minus VI. So V0 is in phase with VI. So the last statement is true. B and D are true. A and B are false. The next question, which of the following statements is true with respect to ideal op amp? Ideal op amp. We have four properties for ideal op amp. Rn is infinity, Rout is 0, AD is infinity, 4 CMRR is infinity. Option A is it has infinite input resistance, which is true. It has an infinite output resistance, which is false. For an ideal op amp, Rout is 0. It has an infinite open loop differential gain. This is true. It has an infinite open loop common mode gain, which is false. Common mode gain ACM will be 0 for a ideal op amp. So here in this question we have to find the upper 3 dB frequency. This is a band pass filter. First we'll find out the transfer function of this. Transfer function V0 by Vi is nothing but minus R2 by R1 or minus Z2 by Z1. Here Z2 is nothing but 2R in parallel with 1 by 0.1 SC. If we simplify, this will comes out to be 2R by 1 plus 0.2 SCR, and Z1 is R plus 1 by 10 SC. Because these two are in series, so Z1 will be 10 SCR plus 1 by 10 SC. So V0 by Vi is minus Z2 by Z1. Z2 is 2R by 1 plus 0.2 SCR times 10 SC by 10 SCR plus 1. So clearly we have a 0 at S is equals to 0, a pole omega P1 at minus 1 by 0.2 RC, and second pole at minus 1 by 10 RC. It is given that lower cutoff frequency is 1 megahertz. We have to find the upper cutoff frequency. So the transfer function will look like this. It has a 0 at omega equals to 0, S is equals to 0. This slope will be 20 dB per decade, and it has a pole at 1 megahertz. At 1 megahertz the slope will be 0 dB, it will be a flat line. And at 10 megahertz at FC2 it has a pole. We have to find what is FC2. This is band pass filter response. This is h of j omega versus omega. Clearly this is minus 0.1 by RC. This is minus 5 by RC. We can see that omega P1 is 50 times omega P2. It is given that omega P2 is 1 megahertz, so omega P1 is 50 megahertz. So this point will be 50 megahertz. So this is a band pass filter response. 1 megahertz to 50 megahertz it will allow, and other frequencies it will not allow. Okay.